I wanted to show you Tianshou reinforcement learning framework by starting off with some basic building blocks. I won't cover all the components, but I'll give you just a taste to entice you to go and explore some more on your own. We're going to talk about batches and replay buffer. Let's start with batch definition. Here's an example of a batch object. Batch objects are like dictionaries. They have keys and they have values. As you can see here, we have 4 keys, A, B, C, D. And each key has a value, in this case 4, array 5, 5, a string of numbers here, and a tuple. Batch is a special concept in Tianshou framework that represents some batch of data, and it's usually collected by interacting with the environment. So first, batch is used to pass the state into the policy, as you can see right here. The collector is something that interacts with the environment and collects some experience. Policy returns its decision as a batch with some special keys like act, for example, for action. And lastly, the collector stores the collected information as a batch in the replay buffer. So as you can see, batch is used throughout the framework to pass data around from component to component. Next, we'll talk about stacking batches. Recall that a batch is just like a dictionary. One of the things that Tianshou adds is the ability to kind of stack these dictionaries, just like you would stack PyTorch tensors. Here we can see 2 different batches with keys A and B. Try to imagine what it would mean to stack these 2 things. Here is the answer. As you can see, if we treat each value as a tensor, this kind of makes sense. A tensor here is stacked with this tensor, results in this larger dimensional tensor. Similar here, we stack 5 and minus 5, and we get a single tensor of 5 minus 5. Let's move on to concatenating batches. We can also concatenate 2 batches together. So try to imagine what it means to concatenate them. Again, think of each value as a tensor here, and we'll just concatenate those tensors. So as you can see, if we concatenate A and A, we'll just get a longer tensor A, and if we concatenate these values B and B, we'll get a larger tensor B. Next component uses circular queues, and if you don't know how they work, it's going to seem really weird, so let's cover that now. Circular queue is an array of some maximum length and 2 pointers, start and end. Initially, both of these pointers are -1. The queue is empty and both pointers point to -1. What happens when we insert a single element? So here we insert the element 3, and as a result we change where both pointers point. In this case, they both point to 0, signifying that a single element is contained in the queue. I'll use the yellow color to indicate the last cell that was modified here. Let's now insert 4, 5, and 6. After we insert these 3 elements, the start pointer still points to index 0, but end pointer now points to 3. So index 0, 1, 2, 3, and this is what the end points to. Now let's insert 3 more elements, 7, 8, 9. Start pointer still points to 0, and end now points to 6. 0, 1, 2, 3, 4, 5, 6. This is the 6th index. So in Tianshou, this circular queue is implemented by a class called replay buffer. Here is how it's implemented in Tianshou. So our replay buffer is just our circular queue. Just like circular queue, replay buffer has a size that's distinct from the elements it contains. So replay buffer has a capacity of 7, but how many items does it contain? It contains 0 items, of course, because we didn't insert anything. Now let's add a single item. In this case, replay buffer accepts batches as items, so let's add a single batch with some dummy keys and values. We'll only worry about the obs key here. So let's add a batch with observation value of 3 and print out what the queue contents are and the length of the queue. So in this case, the contents are this, and the length is now 1. At this point, the number of items contained in replay buffer is 7, and the size is also 7. So our replay buffer is full. So what happens when we add another item? Well, now we have a full circular queue. So what happens when a circular queue is full? Let's look at that first. When circular queue is full, we apply special rules. So in this case, our queue is full. You can see that the start pointer points at 0 and the end pointer points at 6. There are 0, 1, 2, 3, 4, 5, 6, 7 items and 6 indices. So the queue capacity is 7. There are 7 items in the queue. What happens when we add another item? For example, let's add an item 10. Adding 10 wraps around to the beginning of the queue like that and overwrites the first element. So as you can see, number 3 gets overwritten by 10. And it also moves the start pointer over to the next element. So now 4 is the beginning of the queue and start now points to index 1. Let's add another element 11. In this case, you can see it overrides the old start of the queue, which was 4, and the start pointer moves over, now pointing to index 2. So now you understand how a circular queue works, and let's apply the same theory to replay buffer in Tianshou. Let's start with a full replay buffer. We'll initialize our replay buffer with size of 7, and then we'll add 7 items to it. So we'll add a bunch of batches with I ranging from 3, 4 up to and including 9. So these are all the ops values so far. So let's add another batch. Adding another batch with a value of 10, we can see that the first element gets overwritten. So now let's add another batch with a value of 11, and we can see that the next element was overwritten with 11. So when you're looking at these replay buffers inside Tianshou examples, it can be confusing what's happening, but if you think back to circular queue, then everything will be clear. So now that we understand how replay buffers work, let's move on to the interesting part, which is the policy. So how do we use the policy from Tianshou framework? We will use a predefined policy gradient policy from Tianshou. We'll set our learning rate, we'll set our discount factor, we'll create our environment here, we'll get our state and action shapes, we'll create the network, which is our neural network object, we'll create an optimizer, we'll create a distribution, and we'll create a policy. So policy takes the network, the optimizer, the distribution over output actions, and discount factor. So what's this policy object? Policy is some actor that contains a model, and the model in our case is just an MLP. So as you can see, the MLP is defined by 2 linear layers. There are 4 input features and 2 output features. Why is that? Well, if you remember our cart pole, it has some position here where it is. It has some velocity, how fast it is going, left or right. Then it has the angle of the pole, and it has the angular velocity, how fast the pole is falling. So it's a tensor of 4 numbers here. The output features are 2. That means that we can take 2 actions. We can push the cart left or we can push the cart right. So let's see a sample input. In this case, we can see that the state has 4 numbers, as we said. Now let's wrap our observation in a batch. Policy expects a batch object with a special ops key. But why is this value of ops here being passed as an array and not just a regular value? Well, Tianshou works on multiple environments at the same time, so it needs a vector of observations. In this case, we just have a single environment, so we pass just a single element inside this array. So we feed this observation to the policy to get the action, as you can see here. And the action output is a batch. So what are these keys inside here? Well, the logits, that's just the raw output from our neural network. The distribution, this is something from where we can sample our actions. So it might be that we have 2 actions, 0 and 1, and our distribution might be like that. So for this specific input, we might be much more likely to move left. Act is the actual sampled value from this distribution, and the state key is just something that's used for recurrent policies. In this case, we're not going to worry about it. Notice that this distribution object we can use to get the probabilities of actions, or we can just use it to sample an action. By the way, if this sampling action and distribution and logits doesn't make much sense, you should see my video titled Reinforce, where I explain how Reinforce works. So far we have used the policy that comes with Tianshou framework, but how do we build our own? Let's see what it takes to write a custom policy. We will implement the reinforce algorithm in Tianshou framework. So let's create our environment first, so we have something to work with. In this case, we'll work with cart pole. and Tianshou will automatically wrap it in a dummy vector environment. This is to make our environment vectorized. So first, we create a torch network that will be updated by our agent. So this is just a regular PyTorch module. We'll take the state shape and action shape inside our constructor, and we'll use it to construct our neural network here. So cart pole state shape is 4, it's a tuple 4. So this is our state, and the action shape is just 2 because it's a discrete action space. So this expression here will evaluate to just 4, and this expression here will evaluate to just 2. And so we have a neural network with the input size of 4 and the output size of 2. Next, let's define the forward function. So the rules for the custom network forward function is that we have to take an observation, we have to take the state, which is the recurrent state. We're not going to worry about this for now, and some additional information, which we want to worry about as well. So what are the things we have to return? Well, we have to return 2 things. We have to return the logits from our neural network and the hidden state here. We don't use recurrent networks, so we're not gonna worry about that, and we'll just return the same state as before. So how do we use this network that we just built? So first we'll derive a policy, call it reinforce, and we'll derive it from BasePolicy. BasePolicy comes from Tianshou here, and it must contain 2 methods, forward and learn. Inside our constructor, we'll take the network, the optimizer, and the shape of the observation in the action space. We'll pass both of those things to the BasePolicy. Forward method computes an action for a given observation. So given a batch of something as an observation, we want to compute an action. So we get our logits here from our neural network. We'll construct our distribution here using categorical distribution from PyTorch. Then we'll sample our action. Then we'll store the action that we sampled inside the batch that we're going to return. And we'll store our logits as well, so we can reconstruct this distribution in the future. The learn method updates the policy with a given batch of data. So we take some batch of data that already came from interacting with the environment, and the goal of the learn method is to update the policy. So we get a history of actions and rewards that happened during the course of this episode. Then we'll call our forward method that we implemented earlier. Next, we'll evaluate the actions we took using our distribution. So we'll take the actions that already happened and evaluate probability of them using our distribution that we reconstructed using the logits we have stored. Next, we compute the returns at each time step t right here. Next, we'll compute the dot product of our returns and our probabilities. And since we want to maximize it, we'll take the minus of this. Finally, we take the step in the right direction according to our gradient. At the end, we'll return the loss for the logging purposes. So now that we implemented this BasePolicy interface, how do we actually train? We'll import our gym, torch, numpy, and Tianshou. We'll also import a batch and collector objects. I will talk about what this does a bit later. This is the BasePolicy that we implemented. And finally, we'll import a trainer. Let's set some constants. So let's train for maximum 50 epochs. Let's take 1,000 steps per epoch. The maximum number of steps we can take is 50,000. Let's set a batch size of 1. Let's set a learning rate and discount factor. Now let's set maximum buffer size to 20,000. Buffer size won't matter to us because we'll clean out our buffer size after every episode. And as we know, cart poll has a maximum episode length of 200. Whenever the policy makes it to 200th step, it's terminated. Finally, we make an instance of our gym environment. We assemble our things together like a Lego. First, we have our network. Second, we have our policy. And third, we have our trainer. We start with our network. We set our state and action shape. Cart poll has a discrete action shape. Then we create our network and our optimizer. Next, we'll create our custom policy, passing our network into it. We'll also pass the optimizer we created and supply the required state and action shapes. Then we create 2 collectors. So collector is just something that takes a policy and the environment and makes the policy interact with the environment and stores the result in some buffer. So in this case, it's the replay buffer. We will use different collector for training and testing. Again, we set our buffer size to something really large, and it doesn't matter. As long as it's more than 200, it's going to be cleared after every episode. Finally, we create the trainer. We're using onPolicy trainer because we're using the onPolicy URL using reinforce. We pass our policy. We pass a pair of our collectors. We set how much we're willing to train for. We say how many steps we're going to take per epoch. How many times do we want to repeat our gradient update per collect? How many episodes do we want to test? How many episodes do we want to collect at a time? And we'll specify our batch size. So let's now run this and see how the training output looks. So training completes after 50 epochs like we specified. As you can see, we reached the best reward of 200, and this is the maximum possible in the cart poll task. So how do we see our policy in action? Well, we need to evaluate it. To evaluate our policy, we simply collect a few episodes using our trained policy. So we'll just collect 5 episodes and we'll set our frames per second rendering speed. And this will cause Tianshou to render the output of our policy interacting with our environment. And so here we can see our policy balancing the cart poll for 5 episodes. And there you have it. Now you have an introduction to Tianshou framework. Go read more in the docs. I think it's pretty neat framework. In the meantime, if you want to know more about Reinforce, check out my other video. Well, now you know enough about Tianshou to make a great system. Go ahead and do it and enjoy your time. See you later. Bye.